Welcome, this is Coach Dorf. We're in section 4.3 and we're looking at a homework example. In this example, we're given a specific function and then we're supposed to figure out information about the shape of the graph of that function, and we'll use derivatives to do that. All right, so let's begin. So I'm given this function f of x equals 5x cubed minus 3x to the fifth. And the first thing I'm supposed to determine is intervals of increasing and decreasing. So I'm going to write that as intervals of increasing and decreasing, like this. To do that, I just need to find the derivative of the function. And then I'm going to set the derivative equal to 0, and that's going to give me then transition points between when it increases and decreases, or at least possible points, all the possible points where it could transition from increasing or decreasing. So the derivative is 15x squared minus 15x to the fourth, and I want to set that equal to 0. Well, then to solve that for x, I'm going to first factor out what they have in common, which is a 15x squared, and I'm left with a 1 minus x squared. And then I'm going to factor that inside parentheses into 1 minus x and 1 plus x. And so that tells me then that x equals 0, 1, or negative 1. So those are going to be my points that I'm going to use to make my intervals. I'm going to go from negative infinity to my smallest point here. And my smallest point was negative 1. So that's going to be negative 1 there. All right, so that's how I get that point. And then I'm going to go from negative 1 to my next smallest point, which was 0. So that's going to go here. And then I'm going to go from 0 to my next smallest point, which was 1. So that's going to go there. And then I'm going to go from 1. I have no more points, so now I just go 1 to infinity. So I have those 4 intervals. Those represent my x values. And now I want to look at the derivative value on there. Now I'm just going to I can just take any single point in those intervals, evaluate the derivative there, and that will tell me whether it's positive or negative. I just need to know if it's positive or negative. If the derivative is negative, then the function is decreasing. And if the derivative is positive, it's increasing. And I only need to pick those one point because I've already solved it for equal to 0. So everything in those intervals have to have the same values. And that's because of the intermediate value theorem. All right, so here on the first interval, I'm going to just take negative 2. Now, to evaluate that, I'm going to use my factored form, 15x squared, 1 minus x, 1 plus x. And if I plug negative 2 in there for x, I see that this part is going to be positive, this part is positive, and this part is negative. And so a positive times a negative is negative. So this is negative because that's less than 0. I'm going to do that for all the points, all the intervals. Here I would take negative 1/2. Here I'm going to take positive 1/2, and here I'm going to take positive 2. And again, I just look at the value of my derivative at those points here. Here I'm going to get a positive value. Here I'm going to get a positive value, and here I get a positive value. So that's greater than 0. So I'm going to put a plus there. And likewise, if I keep doing this, I'll get plus and minus. All right. So what does that tell me? So then interval of increase is when the derivative is positive. And so that's going to be negative 1 to 0, union 0 to 1. Now I could also write that just as negative 1 to 1. Either one is correct. And then the interval of decrease is the intervals where the derivative is negative, and so that's going to be negative infinity to negative 1, union 1 to infinity. All right, so that was our first part A. Part B, we're supposed to find local max and min values. All right. What I would do to this one is I would just look at my intervals of increasing and decreasing. Okay. So I know that, again, if I were to make my table, let me make my little table here. I've got negative infinity to -1, I've got -1 to 0, 0 to 1, and 1 to infinity. And we showed earlier that here on this interval, it's decreasing, and then it's increasing, increasing, and decreasing. Okay, so this is like intervals of increasing or decreasing. Now, if something is decreasing, it's going down, and then if it's increasing afterwards, it's going up. That's going to give me a local min. So there's a, this tells me there's a local min at x equals -1. Well, in the next part, from -1 to 0 and 0 to 1, it's increasing and then increasing again. So there's not a local min or max because it's keep going up. But from here to here, from 0 to 1, it's increasing, and then from 1 to infinity, it's decreasing. So that must be a local max because I'm increasing, decreasing. So there's a local max at x equals 1. Now, the problem asked me to find the local max values. What I found is the x value, but I really need to find the y value, or the f of x value. So the local max value is f at 1. All right, and I get the 1 because I take this value here and I put it into the function. All right, and so I evaluate that. Again, remember that my function is, just as a reminder here, was 5x cubed minus 3x to the 5th. That was our function. So f of 1 would be 5 times 1 cubed minus 3 times 1 to the 5th, and that's going to equal 2. So that's a local max value. Local min value is going to be f at -1. And again, I get that -1 because I take my local min value there and I plug it into the function. And when I do that, I'm now going to have 5 -1 cubed minus 3 times -1 to the 5th. And that's going to give me a -2. So I have a local min value at -2. Make sure you see the difference between the local min at x equals -1 and the local min value of -2. All right, the next part was to find intervals of concave up and concave down and in any inflection points. All right, so how do I find concave up and concave down? I take the second derivative. So again, our function was 5x cubed minus 3x to the 5th. Our first derivative that we did in part A was 15x squared minus 15x to the 4th. Now we need the second derivative to find concave up and concave down. So I'm going to take the derivative of the first derivative, and I get 30x minus 60x cubed. And I want to set that equal to 0. To figure out the x values for which that works, I'm going to factor out what they have in common. So both terms have a 30x. So I'm going to have 1 minus 2x squared equals 0. Now, it may not seem like this is easy to do, but I can factor that 1 minus 2x squared into 1 minus square root of 2x and 1 plus square root of 2x. And so that tells me that my points where the second derivative equals 0 are 0 and 1 over square root of 2 and -1 over square root of 2. All right, just so everyone's clear on this, if I set this one equal to 0, I have 1 minus square root of 2x equals 0. Then if I bring the square root of 2 to the other side, that's going to give me 1 equals square root of 2x. Divide both sides by square root of 2, and I get 1 over square root of 2 equals x. And that's how I get this value there. Okay, just like in part A now, this gives us the endpoints for some intervals. So we're going to make a set of intervals, and then we're going to see whether the second derivative is positive or negative on these intervals. And that will then inform us whether the function is concave up or concave down on those intervals. So my intervals are going to be negative infinity to the smallest number, which was negative 1 over square root of 2. And then I get the next one, the next interval, which is going to be negative 1 over square root of 2, to the next smallest number, which is 0. So that's 0 there. And then I'm going to go 0 to my next smallest number, which is 1 over square root of 2. Okay, so that goes there. And then I have no more numbers, and so I'll go off to infinity there. And so this becomes my table. And these are my x values going across. And now I want to look at the second derivative, because the second derivative tells me information about concave up and concave down. And just like before, all I need to do is take a point inside each interval and find out the value of the second derivative, whether it's positive or negative. So here, it's good to know that negative 1 over square root of 2, what's that approximately equal to? 1 over square root of 2 is approximately 0.7. So this is going to be approximately negative 0.7. So I'm going to take a value here of like negative 1. And again, I'm going to write down my second derivative in its factored form. So that was what I had right up here. I'm going to use that form down here. So I have 30x, 1 minus square root of 2x, 1 plus square root of 2x. And so if I do the second derivative at negative 1 here, I'm going to get a negative number. Here, I'm going to get a positive number. And here, I'm going to get a negative number. And so all those multiplied together is going to give me something greater than 0. So this is going to be a positive number here. For the second derivative here, I want to pick a number between negative 1 over square root of 2 and 0. This is a little bit difficult, but I'm going to just take negative 1 over 10. Because again, I remember negative 1 over square root of 2 is negative 0.7 approximately. So negative 1 over 10 works really well. If I do that and do the same process I've done before, I'm going to get a negative here. And then here, I'm going to take 1/10. I get a positive. And here, I'm going to take the second derivative at 1, and I get a negative. All right. So what do I know about concave up with these signs? Well, my favorite technique for this is second derivative. So I've got 2 of the symbols. If it's positive, I have 2 of those, and that's my smiley face. And this shape is concave up. All right, so anywhere I have the second derivative is positive, I have concave up. So the intervals of concave up are negative infinity to negative 1 over square root of 2. All right, and that's coming from this part right here because it's positive. And then union. And where else do I have positive? I have positive right here. So I take this interval, and that interval was 0 to 1 over square root of 2. And then likewise, I can do intervals of concave down. Just as a review, concave down, second derivative, if I have negative, so I'm going to write 2 symbols because I have second derivative 2 symbols. Okay, that's frowny face or stormtrooper, and that is the concave down mouth. All right, so anywhere I have a negative, I've got concave down. So here I've got concave down on this one and this one. So I'm going to do negative 1 over square root of 2 to 0, union 1 over square root of 2 to infinity. All right, those give me then my intervals of concavity. And now we have to do inflection points. And what are inflection points? Okay, well, inflection points are when it changes from concave up to concave down or concave down to concave up. Well, we can see here that those happen, those signs change at negative, let's see, I gotta get a good color here. Let's do purple. At negative 1 over square root of 2, it changes from concave up, from negative to positive, so concave up to concave down. And so we have x equals negative 1 over square root of 2. Likewise, I have that at 0 and at 1 over square root of 2, because in each case, the second derivative changes from plus to minus or minus to plus. All right. Now, they want an inflection point. They don't want just the x value, so I need to figure out what is f at these points. So f at negative 1 over square root of 2. I'll plug that back into my original equation. Again, remember f of x was 5x cubed minus 3x to the fifth. So I'm going to get 5 negative 1 over square root of 2 cubed minus 3 over negative 1 times negative 1 over square root of 2 to the fifth. And when I simplify that, I get the answer of negative 7 over 4 square root of 2. All right. So one of my inflection points is going to have that as the y value. And I can solve these other ones, f of 0. Where am I getting the 0 from? That's coming from here, my second one. So I'm going to look at that. 0 there. If I put that in, I'm going to get a 0. That one's pretty straightforward. And likewise, if I do the last point here, f of 1 over square root of 2, there's going to be a symmetry here. And that one's going to equal positive 7 over 4 square root of 2. So my inflection points are going to be, negative 1 over square root of 2, comma, negative 7 over 4 square root of 2, 0, 0, and 1 over square root of 2, comma, 7, 4 over square root of 2. All right, so I've got my concaves up and I've got my inflection points. And then the last thing it asks me to do is to sketch a graph of this. So I can use all this information I have here, draw an axis here. This is the y-axis, this is the x-axis. And using all the information I have here, I know I have an inflection point here. I have a minimum, a local min here. This was a local min. This was an inflection point. I had a local max here. Okay, and then we got that in part B. The local max and local min are from part B. I also have an inflection point that is approximately about here. So that's an inflection point. And there's an inflection point about here. And that all came from part C that we did. And then in part A, we know that it was decreasing until we got to negative 1. This is exactly supposed to be at, oops, sorry. Okay, let me redo that here. It's decreasing to here. And then it's increasing. Okay, and then it continues to increase here, up all the way up there, and then it's decreasing again. And now I have to check my concavity. It's supposed to be concave up, okay, from here to here, then concave down here, then concave up here, and then concave down here. So that matches what I got in part C, and that's what the graph, sketch of the graph looks like.